the loads.
Jindal, very good. We cannot use this because there is a what? Okay, there's an axial load, therefore the above equation is not valid. Okay, so you cannot use this equation, right? When we do our shaft design, we assume that we assume that there's no axial load. But for this case, we have 2,500 pounds. Okay, so that's why we cannot use that. Okay, so now let's go into structure analysis now. Okay, so first thing of all, we're going to draw our transformation, right? So this is our stress X. Oh, this is our X direction, right? This is our Y direction. And over here, this is our Z direction. Okay, so X, Y, and Z. Okay, so we can see that, right? We can see that our let's look at our load first. Okay, so we have our PX is equal to minus 2,500 pounds, right? And then we have a torque in the X direction. Okay, so torque in the X direction is equal to 2,300. Then we have to multiply by 12. Why multiply by 12? Because we have to change everything into inches. Because why everything in inches? Because our stresses in pounds per square what inch. Okay, so 2300. So it's 27600 pound inch. And then we have moment in the Z direction. Is equal to 1,500 multiply by 12, so 1,500. So it's equal to 18,000. Right. So we are going to look at 4 different positions where to calculate the bleh, I'm being tongue tied now. Where to calculate, okay, at what position of the shaft. We have to know where is undergoing maximum stress. Okay. So I'm going to label this. Yeah, I'm going to draw elements now. I'm going to draw elements. So this is my element A. No, this is not a very good. Wait. So this is my at the top. Okay, let me. So over here, this is my element A. Okay, and then I'm going to have my element B. At the bottom is my element C, and over here is my element D. Now bear with me. Some of you like ask you, Eugene, what are you doing down here? Okay, so that's how I'm going to label our elements. Okay, we have to analyze where is the element that has the maximum stress. Okay, now we don't know. Yeah, I'm going to copy this. So there are two formulas over here. Okay, there are two formulas that we can use over here. Okay, there are two formulas. So we have the shearing stress, right, is equal to Tx divided by J multiplied by C. Okay, where C is the radius of the shaft. Okay, and then we have a normal stress, right? We have a normal stress in the x direction, which is contributed by the axial load, which is minus px over a, right? And a is the cross sectional area of the shaft. Right? And then we also know that stress X is also equal to mz divided by izz, right? Multiplied by y, and we know that y corresponds to the radius of the shaft. Okay, so remember what I told you, based on bending, below the line or the head of the arrow is compression, on top above is going to what? Tensile, right? Above going to tensile. Okay, so now we are going to look at, now we there's nothing that we can look on the shear. If we were to look at on the shear, so okay, if there is a shearing force, okay, we have to consider the shear stress is equal to Vy over Izz Qz divided by T. Okay, but for our case, there is no what shearing stress at all. Okay, for our case, it happened to be we did not know the shearing force. Okay, so now I'm going to look at the shaft from the front view now. Okay, so I'm going to have a shaft from the front view now. So this is, I'm drawing, this is Y, this is our Z, and this is rotation of X. Okay, so I'm going to draw the front view. Okay, so this is our shaft. Okay, so at this position over here, right, that is our neutral axis. Right, so this is I'll draw our elements. Okay, we have element here, element here, element here. So this is your element A, element B, element C, element D. Okay, so now let's look at I'm going to divide them into 4 different positions. Now we are doing analysis because we don't know which element to calculate yet. Okay, we have to know which element to choose. Now we don't know yet. Okay, you cannot say let's do all. No. This is the part that you get marks. This is the analysis part. Okay. So we will have our element A, element B, element C, and element D. Okay. So we are going to look at different aspects of the stress field now. Okay, we're going to look at different aspects of stress field. So the first one we will look at, let's look at Px over A. So stress X is equal to Px over A, right? So this is due to axial loading. And if you look at the axial load is minus 2,500. So they are all minus what? Minus Px over A minus Px over A. They are all going to see the same thing. Okay. So some of you might say, Eugene, if that's the case, we calculate. Oh, no. Then the next one, we're going to look at stress X. Right, stress X. Now this one is going to be equal to mz over izz multiplied by y. Okay. So we know that stress A, right? So we know that the moment the arrow is going this way, right? So this is our moment in Z, compression and tensile, right? So element A will be positive, right? Or positive. I'm going to write up the formula. It's going to be equal to positive mz over izz by y multiplied by y. At point B, the y position is equal to 0, right? At point C is equal to minus mz over izz and y. And then point D is equal to what? 0. Okay. Now I'm going to go further. Okay, I'm going to go further. Now this load is not there. If it's there, okay. So now let's say now we have, okay. So mx stress x. Again, this is equal to my over iyy multiplied by z. Okay. So for example, this is not there. Okay, but I'm just giving you an example. So for example, now if we have another load over here, a moment, right? So this is our moment in y, and then this is compression, right? And this is tensile, right? So if you look at point A now, right, is equal to 0. As I say, this is not there, okay, but I'm just giving you an example if it's there, okay? And then point B, right? Point B is equal to point B is equal to compression, so minus my over iyy multiplied by z, right? And at point C, right? Point C is again at is neutral axis. It's equal to 0, and point D will be tensile plus by my over iyz. Okay. Now, if we were to look at shearing stress, okay. So if we now I know this example don't have shearing stress. I want to put everything in so you can analyze. Or let's look at shear first. Okay, let's shear. So the shear due to the torsion is equal to Tx C over J, right? And all of them will have the same number. Okay, so Tx C over J, right? Tx C over J, all of them will have it. Because the torque is felt by all the elements. Okay. So now let's do something that is going to be it's not there in this question. So what is not there in the question, I'll do in pink. Okay. So now, what if now, right?